Hi everyone, I'm Giuseppe Laera, a PhD student from Alset Lab at Rensselaer Polytechnic Institute, and I'm going to present our work about guidelines and use cases for power systems dynamic modeling and model verification using Modelica and OpenMPSL. Here you have an overview of the presentation. After an introduction of this work, the motivations and contributions are presented. Then a description of the guidelines for power system models, implementation and validation is given. The considered reference tool is PSSE. After that, some challenging and interesting use cases are presented, highlighting some difficulties faced in the re-implementation process from PSSE to Modelica. In this section, examples of interoperability are also illustrated. Finally, some conclusions and future work to expand this are described. One of the goals of the paper is to formalize the process of power systems dynamic modeling and model verification using the Modelica language and OpenMPSL. The description of the steps for complete re-implementation of power systems components of a closed-source commercial software like PSSE are described. Some challenging use cases are presented to highlight the value of the proposed approaches for model implementation and validation. Also, the advantages of self-documenting nature of object-oriented equation-based modeling offered by Modelica are shown. The existing modeling tools are not always transparent in the dynamic behavior description. The open access standardized Modelica specification enables open access standards-based interoperability. So models don't have to be re-implemented to be utilized in different Modelica standard compliant tools. A generic methodology for re-implementing existing models from different software tools and domains can be derived from the proposed steps. To help all the players of the electric power system sector to perform their studies and analysis, over the last decades, several software tools have been developed. The traditional tools used by industry include proprietary software like PSSE, PSCAD, EMTPRV, Power Factory, etc., that require the user to become an expert of their functionalities to be productive. Each tool has its own way of defining the data used to characterize their discretized model. So those tools are not flexible when attempting to share models and data in other software environments. Another drawback is represented by the inconsistency of dynamic simulation results between different simulation platforms. This is due to the need to re-implement models in each simulation platform, which has tremendous costs. The idea to remove ambiguity in power systems modeling was introduced by using the object-oriented equation-based modeling language Modelica. Following this innovative idea, a power systems library called OpenMPSL has been developed. The library continues to be maintained and expanded based on the concepts of regression testing and continuous integration that allow the models to be verified against a traditional commercial software tool like PSSE. In this way, the user of the power systems community gains more confidence about the reliability of the library for performing dynamic simulations and studies. A formal description of the model implementation approach used for component model development in Modelica to meet the requirements of the power industry is presented. Also, the software-to-software model validation process against the reference domain-specific tool PSSE is described. The use of the object-oriented equation-based modeling language Modelica allows for unambiguous power systems modeling. The flexibility of the language offers options to model a component, either by using typical block diagram representations or by defining mathematical equations that describe its dynamic behavior. The classical approach to validate a component's dynamics is by creating a small reference power network model, like a single machine infinite bus system, SMIB. Using the Modelica language, it is also possible to validate each individual subsystem component within a model by using the reference tool's output signals and connecting them to the inputs of the newly implemented model. This simplifies the modeling process, as it allows to isolate the specific component that is being implemented in Modelica, instead of having to use it in a small reference power network as it is necessary for the traditional software tools to perform simulations. Some challenging use cases are presented to illustrate the proposed approach that is also summarized with flowcharts. A basic example of electric power system network is the SMIB, used to model a power plant with its controls connected to the rest of the grid through transmission lines and substations represented by buses. This small network also defines the model to standardize the testing of different device models implemented in Modelica and having PSSE models as reference. In the figure of this slide, in the red block, a complete power plant is modeled with the generator connected to bus Gen 1 and its controls. The grid is represented by the generator connected to bus Gen 2. Between Gen 1 and Gen 2, other power systems components are considered like lines, a load, and a ground fault. The bus shunt also allows to connect other components to this small network. Depending on the type of power systems component to model, the configuration of the generating unit in the red block connected to bus Gen 1 varies, whereas the configuration of the rest of the network in the green block remains the same. The process of implementation starts with the assignment of a model to implement. The identification of available technical information about the model is necessary for its implementation in Modelica. If the PSSE manuals do not present sufficient information about the model's dynamics, then it is necessary to find additional literature that can help understanding its behavior in the reference tool. Once the documents describing the model have been identified, collected, and analyzed by finding the block diagrams and/or the equations of the model, it is possible to determine if the building blocks of the model are already present in the OpenAPSL library. It might be required to implement missing blocks or functions before building the entire component model with the appropriate initialization of its subblocks. To assess the validity of the model to implement, a small test network SMIB is used in both Modelica and the reference software PSSE. The reference results from PSSE have to be generated. The SMIB network with the target model needs to be assembled both in PSSE and Modelica. After that, the software-to-software validation can be performed, following the model validation guide of the following slide. After assembling the SMIB in PSSE, it is necessary to obtain the steady-state computation results of a power flow, export them, and provide them as initial guess values to solve the initialization problem of the corresponding SMIB in the Modelica compliant software tool. The OpenAPSL library used in this validation process describes the dynamic behavior of power system components. Therefore, it relies on external tools for the power flow calculations necessary for initializing the models. The import of the power flow results can be made manually or automatically, increasing numerical accuracy and reducing human errors. Next, the scenario for the dynamic simulation in both tools can be defined, and the dynamic simulation of the SMIB in both softwares can be run. Once the results are generated, the quantities to compare can be chosen and exported in the appropriate format to be used in another tool, like for example CSV Compare, that allows to quantify the discrepancies between the simulation software tools after defining an acceptable tolerance level. If the errors between the quantities to compare are within the tolerance band, then the validation is complete. If the errors are bigger than the defined tolerance, then more debugging of the model is required. A better insight of the model dynamics can be obtained by comparing subcomponent inputs, outputs, and states with the analogous signals from the SMIB PSSE. The iterative process continues until the difference between signals is lower than the tolerance, meaning that the validation is completed. This process can be part of a continuous integration and regression methodology. In this part of the presentation, some key use cases of the implementation of power system components are described, following the steps of the previous slides. The verification illustrated through the plots of some quantities includes a software-to-software validation between PSSE and different Modelica compliant platforms. An example of the difficulties faced when implementing a standard power system model, like a power system stabilizer PSS2A, is given in the coming slides. The reference software tool PSSE comes with several manuals to help understanding the implementation and behavior of the different components present in its libraries. In some cases, like for this PSS model, the documentation is insufficient and not helpful to understand the behavior of one of its subblocks, that is the run tracking filter. An initial implementation of the run tracking filter in Modelica revealed to be not accurate compared to PSSE implementation. This result led to additional investigations about the run tracking filter block. Because the PSSE documentation does not offer more details, then the idea of analyzing the continuous time trajectories of the states of this block was used. This idea was derived considering the available information that needs to be appropriately selected, included in the simulation results of an SMIB test system in PSSE with the model PSS2A. So from PSSE, it is possible to analyze the dynamics of the run tracking filter block through its input, output, and states. A visual illustration of the implemented corrections when the filter model was debugged is given in this slide. The model of the RAM tracking filter has been implemented with a code using several features of the Modelica language. In particular, the creation of arrays of transfer functions has been used to build the model. In this way, a transparent and self-documented implementation without leaving any uncertainty about the dynamics of the component was obtained. The implementation of the RAM tracking filter has been tested first with the component alone. Then the component has been introduced into the PSS model of PSS2A that has been tested in SMIB, like in the networks of this slide. A multi-platform software-to-software validation of PSS2A in a SMIB system with the scenario of three-phase fault to ground applied a bus fault at time t equal to seconds for 0.15 seconds is given in this slide. The simulation in the different tools have been performed with the same tolerance and the same output interval length. The same type of simulation with the same settings will be used in the coming slides if not otherwise specified. Another use case is represented by the implementation of the exciter model DC4B. The challenge of this example was represented by the integrator block inside the PID with non-wind-up limits. In this case, to find the right representation of the dynamics of the PID block, it has been necessary to check the state of the integrator. The interpretation has been facilitated by observing the output of the PID block together with the state of the integrator of the PID during a dynamic simulation of the SMIB with DC4B in PSSE. This is illustrated in the plot on the right. When the output of the PID reaches its limits, the state of the integrator, so-called conditional integrator, freezes to avoid wind-up effects. This observation led to the Modelica implementation of the following slide. Here you have the Modelica models of DC4B and its PID. On the right, a block diagram of DC4B, and on the left, more details about the implementation of the PID block. A software-to-software validation of DC4B in a SMIB system is given in this slide. The simulation performed in this case has the same settings described in the previous case. The simulations in both tools have been performed with the same tolerance and the same output interval length. An alternative approach for the validation of the DC4B excitation system, taking advantage of the Modelica flexibility, consists of simulating only the block representing the DC4B component driven by external input signals collected from the reference SMIB network in PSSE. This means that the Modelica model of DC4B can also be run using different input signals coming, for example, from real measurements. To prove this new approach, the PID model has been modified, replacing the integrator blocks with an input, so to use the integrator state trajectory as input to the model, as shown at the bottom of this slide. Instead of assembling an SMIB to test the new implemented model, it is possible to build a test system with only the target model, with all the inputs depending on the available signals, and a table collecting the external signals driving the model. The software-to-software validation of DC4B is performed considering a simulation with similar settings as in the previous examples. The output of the exciter coming from the same simulation scenario has been compared between different configurations, and they are SMIB with the considered exciter model in PSSE, SMIB with the considered exciter model in Modelica, and test system illustrated in the previous slide with the exciter alone. Finally, to demonstrate an additional value of implementing and validating models with the Modelica language, we highlight the portability of system models using validated components. This can be shown by running the simulation of an example of the OpenAPSL library in different software environments. The example of an SMIB with the exciter EXST1 has been chosen. The plots show that the model gives the same results regardless of the tool being used, which means that tool-specific reimplementation can be avoided. Another example is the network model IEEE14. A simulation of the network has been run in the reference tool PSSE and for different platforms that are Modelica based. The same scenario has been considered in all softwares, and it consists of applying a three-phase fault to ground at bus 4 at time t equal 3 seconds for 0 seconds. The same simulation settings about the output interval length and the tolerance have been used. It is possible to see that once the models are validated, they can give the same results as the reference tool with the same simulation settings, even for larger networks. Summarizing the work, we can say, this paper formalizes and illustrates a procedure to implement power system models in Modelica with a software-to-software validation methodology. The described steps are important for developing and maintaining a Modelica library using the concepts of regression testing and continuous integration. The guidelines illustrated in this paper are indispensable for the initial debugging of new models, addressing all possible challenges of the time-consuming reimplementation process in a systematic way. Challenging key use cases were provided to give an idea of the difficulties faced when developing power system models from a reference software tool. Finally, once the results of an initial validation are satisfactory, then the software-to-software validation process can be automated, using scripts to test different scenarios in the different simulation platforms. Thank you for your attention.